Thank you very much for this kind introduction, and thank you to Carlo and for the organizers for inviting me to come and give this talk. I actually really looked forward to it because I always find it interesting to convey such information to other groups of people than, normally like I do at EGU for some scientists. So I've tried to keep it on like simple high level, but really the way I've organized it is to show how the science is actually used for applications, and then in parallel how I hope I can inspire you to use the subject of space weather for educational purposes. So with this, I will begin now formally the lecture. So I always like this cartoon because it's the oldest space weather cartoon that I've been able to find in the literature. It was a special issue in '62 concerning solar activity, and one of the papers by Goldberg concerned solar activity. And already then they had this idea that somehow we were connected, with the sun. They knew something was going on. And here you see their idea of particles streaming down from the sun, interacting with Earth that's trying to protect herself with an umbrella. So of course, from then to now, we have come a lot further with the space era. So today I will talk about another type of natural hazard. You've already heard about many types here on Earth. I say avalanches, one can say in quotation marks, earthquakes, volcanoes. So I'm going to talk about avalanches in space, so solar storms. And to do this, I will talk about the subject space weather, okay? So the outline of my talk is such that first I will give a brief introduction to what space weather is. And then the second part, which will be about 10-15 minutes, I will try to go quickly through the subject matter because I would have loved to have a week. There's so much interesting things to say. But the second part is 2 examples of some educational things that I do for children with space weather. So I would like to share with you. So first, what is space weather? Basically, there are many official definitions of space weather, but again, I like to keep things simple. So space weather is basically how solar activity may have unwanted effects on technical systems, and that can be it in space and even down on the ground. Here are some examples. And human activity, and this is mainly, of course, like astronauts and cosmonauts going out to space. Now, the space weather, in general, one can say is a function of 3 issues. Where we are located in the solar system. Why is that? It's because the sun, one can say, is the driver of the space weather, okay? So it's the activity of the sun that changes the day-to-day, the minute-to-minute activity, the characteristics of the space environment where we are located. So basically, any solar system, any star system, one could say, remember, you all know, the sun is a star, will have its local space weather. So I already mentioned the behavior of the sun. The sun has this 11-year solar cycle, solar maximum, where there's lots of activity. You hear about phenomena in the news like coronal mass ejection, solar flares, sunspots, a lot of sunspots. I'll tell you show some examples of those in the next slides. And then you have the decay phase, and what we see here are X-ray spatial images of the sun taken from the Japanese Yoko satellite. And you can see when there's a lot, these are color-coded images, okay, the red. It's not emitting red, but it's the way we use to actually be able to see better when there's activity. So when there's white, there's lots of activity, and when it's darker, there's no such activity. So that would be like solar minimum. And then finally, for us, concerning us, the Earth has a magnetic field that protects us basically from the solar wind that comes continuously from the sun. And any other planet, if it has a magnetic field or if it has an atmosphere, all of that also defines the local space weather. So I already mentioned the solar wind. So on the left side there, so basically the sun is rotating. And when it does that, the magnetic field, the sun is a plasma, so the 4th state of matter, so the magnetic field lines also, it all rotates. And from that, you'll have this interplanetary magnetic field that gets thrown from the sun. And it's then embedded, one can say, in the solar wind, which is made up of low-energy particles, basically protons and electrons. In this solar wind that continually, from all directions, okay, from the sun, okay, it will, of course, hit the Earth at some point. And that's what actually creates this magnetosphere, as we call it. So when it comes, if it was ideal, you would have a dipole, the magnetic field around the Earth. But of course, nature is not always so ideal. So what it does is the solar wind, it like pushes it in. This is why you have this effect. And then it pushes it out. So you have what they call the magnetotail. Okay. So you have the solar wind all the time at different levels, sometimes stronger. You have a high-speed solar wind sometimes, but you always have this low-speed solar wind. In the solar wind also, you'll have, as I said, solar flares, coronal mass ejections, and as a function of these two phenomena, you also have something called solar energetic particles. And it's actually these three phenomena, which I will show you some examples of. And basically, all of this, one can say, is solar storms, because usually you're not going to just have a solar flare. When it's these big solar storms, I have a lot of flares, some CMEs, some solar energetic particle events occurring at the same time. So a solar storm is humongous activity, but of course you can also have periods where you maybe just have a small solar flare. But that's not so interesting for this lecture. This plot, so what it shows is the x-axis is, one can say, the time, okay? So phenomenon like radio and X-rays, so when you have solar flares, for example, they emit in different radiations of the electromagnetic spectrum, I'll come back to. And of course, that travels with the speed of light. So in your 8 minutes, you'll already be able to detect that at Earth. So it's like a warning, one can say. You also have the solar particles. They travel the fastest, almost at the speed of light. So basically, so normally around up to 15, 20 minutes. These are really the dangerous ones, but they can also take some days, the slower ones. And then we have the solar wind disturbances, and these are like the coronal mass ejections, and they can take up to days to reach Earth. And finally, here the recurrent activity, what this means is the sun, as I mentioned, rotates, and on average, it's 27 days for one rotation. So if you have a big sunspot that keeps surviving as strong, you actually can forecast then that it will come around again and that you should take care of that. Maybe there will be another big solar flare. Okay? Of course, with space weather, it's not just science, as I mentioned. There's also the effects of the space weather. So this is why I call it science and effects. This view graph in itself, I can talk about it for an hour. I won't, but what it does, Lanzarote has made a really nice overview of all the different systems that can be affected by the space weather. So up in space, you have satellites, for example, themselves that can get charged when there are lots of particles. You can also have solar cell damage. That's when like individual high energy particles come and actually can deteriorate the solar cells over time. Then if we go further down into the ionospheric of the Earth, when you have magnetic storms, I'll come back to it also, you will actually, the ionosphere will change in density. And as we know, we communicate with many satellites to transfer like signals, right? Like GPS also, things like that. So these types of things have to be taken into consideration. There are algorithms that actually can correct for some of these density irregularities, but sometimes they're so intense that actually things don't work. So this is why, so these are like these ionospheric currents, plasma bubbles, these are like irregularities. And as I mentioned, the radio wave disturbances, signal scintillations, there are many different types of technical phenomena. And then, because people always ask, airline, what do we mean here? These are basically the airlines on high altitudes, high latitudes that cross, let's pretend we're flying from New York to Hong Kong. actually rely on high frequency communications. And if you have a big solar storm, that won't work very efficiently, and then they have to reroute. And then on the ground, we have something, a phenomenon called geomagnetic induced currents that I will show as an example later. But just to say, this is really a global phenomenon that affects us all either directly or indirectly. So now I come to my 3 examples of these physical phenomena. So first of all, solar flares. So what are these solar flares? This is a little spot on the sun, okay? But it shows actually a solar flare going on. As you can see, this solar flare is huge. It actually saturates the detector. That's what you see at the end there. The white is. So solar flares are defined as sudden, rapid, intense variations in brightness. They occur when basically magnetic energy, so remember the sun is a plasma, so it's like magnetic fields there, has been built up, and you have something called magnetic reconnection. Very simply, the analogy is pretend your magnetic field lines are rubber bands, and you twist them, and at some point they reach a stress level, and then they break. That's basically what magnetic reconnection is. And when this energy is released, it's heated, and particle beams are also accelerated in the solar atmosphere. And that's why you actually, with these particles, you see these radiation in the electromagnetic spectrum in different wavelengths from radio all the way to gamma rays. Okay? Also, please remember again, these are color-coded images, okay? But again, to show more strongly what it is that's occurring. So I always like to show this graph. I also show it in my lectures when talks for sciences, because people have this tendency to say radiation. I'm like, yeah, but what type of radiation? Because there are 2 types. You have your charged particle radiation, and this can be electrons, protons, so these are particles. And then you have electromagnetic radiation that we all are familiar with. These are the photons that are transferred at different electromagnetic waves. Okay? There's a lot of information on this view graph, but what I want to show with it, actually, you can also simplify it, make a more simple picture, but it's a way to teach if you're, let's pretend, high school level. I quite remember when we learned about the electromagnetic spectrum, but it's a way to show different energy wavelengths show different characteristics of the sun. So at the X-rays, you are up in the solar corona. This is where it's the hottest, okay? And that's where the X-rays are emitted. And then when you go further down, for example, on the chromosphere, this is where infrared radiation is absorbed and where you see features in the infrared. And then down on the photosphere in white light, you see, for example, the sunspots. So actually, if you have images in all the wavelengths, you can actually follow the story of the solar activity. And this is what space weather forecasters do, actually. They look at all these images and try to deduce what actually happened and what will happen. Here's a typical slide of data. Okay? So this is one of the famous Halloween events. Many have heard of. This was in 2003. It happened during Halloween period, so that's why it's called Halloween event. As you see from the 28th October to begin here at the end of October, these are X-ray observations, okay, in watts per meter there. And what you see, so basically it integrates the whole X-ray image of the sun. This is not spatial image, it's an integration of all the X-rays coming out. And you see this is like the background level, and then suddenly you have an intense X-ray, again down background, and there's lots of intense X-rays during that period. And what they found that they were the 2 most intense are actually associated with 2 front halo coronal mass ejections. So next slides I show coronal mass ejection, but these are these big blobs of plasma that get thrown out, and a forward means it's directly thrown towards Earth. So there you see there is a connection between the flares and the coronal mass ejections. And finally on top, this is actually a time scale on the x-axis, and the y, this is the particle flux, the proton flux that is observed. And you see you have the background in the beginning, and suddenly there's this huge proton event. And we know it's associated with both the flares and the coronal mass ejections. Basically, with the flare, it's more probably the start of it, because these are more the very intense but short duration particle events, some minutes to hours. Whereas with the coronal mass ejection, there's when it moves, it creates a shock, and that shock will actually accelerate particles. And this can take hours to days. And that's why you see this event actually lasts quite a while, okay? Now, the electromagnetic radiation from the sun, we can learn about what's going on, the solar activity, but actually the same radiation can also cause problems on Earth. This is an example. Many of you remember Skylab, one of the first space stations. And actually it was emissions from the sun in X-rays and ultraviolet that caused the upper atmosphere of Earth to heat up and expand. And actually some scientists miscalculated a bit the time of re-entry of Skylab. And the thing was, because of this heating, Skylab its altitude started to fall because the density of the atmosphere changed. And basically it was space weather that caused the failure of Skylab. It's just to show one huge flare, solar activity can actually cause these problems. Now people are much more aware of this, of course, and there's whole dynamic models of the ionosphere that take care of these things. But there are still surprises when there are these sudden solar storms and satellites change orbits and small particles actually that's also a big problem. But that's debris, something else, which we can always discuss afterwards. So, example 2, so these coronal mass ejections. So what are they? They are powerful eruptions on the sun's surface. Again, they are also caused by instabilities in the sun's magnetic field. And these enormous bubbles of plasma, when they leave, they travel from 100 to 2,000 kilometers per second. So you see they are a bit slower than, for example, the high energy particles. And here's an example. Let me just click. Should work. Hopefully. Yes. You see these? Yeah. Let me plug again. So what actually, this type of detector is called a coronagraph. It's an artificial eclipse. So you all know when the moon covers the sun, you actually are able to, you should never look at of course, the corona during eclipse. But you see the more light part of the solar atmosphere. So what we do, we make artificial eclipses. So basically this part here blocks the brightest part of the sun, and then you are able to see what goes on. And that's how we can see, we are able to see these coronal mass ejections. So this blob coming out, this is not a front halo CME, this is like a side. This is why we can actually see them. So they'll go this way. And when you see all the particles, that's actually these solar energetic particle events that are caused by the shock of the CME. And they actually cause problems for the detector because they contaminate basically the image at the end. Now CMEs can cause a phenomenon called geomagnetic storms. So you have your CME that flows slowly here to Earth. It hits the magnetosphere, and the magnetosphere gets completely perturbed and confused. And this is, so basically a geomagnetic storm is a temporary disturbance in the Earth's magnetosphere caused by solar wind disturbances. And the main disturbance is the coronal mass ejection. Now, these types of storms, they can perturb also the ionosphere, causing problems, as I mentioned before, like GPS, navigation, satellite communications, and high frequency radio communications. And this was like the polar route airplanes I talked about. Okay. Now, they can even go further, these geomagnetic storms. There's a phenomenon called geomagnetically induced currents. We like to say they're the ground end of the space weather chain. And they are produced by enhanced currents that flow, so in the magnetosphere, ionosphere, during these geomagnetic storms. So at high level, you have currents, and then they induce other currents, and these currents, in the end, can be actually induced on Earth. Okay, and these can have consequences for electrical power transmission systems, oils, and pipelines. So the current can actually flow through these pipelines, cause corrosion effects if the pipeline is not grounded correctly. And for the electrical industry, they can lead to a loss of reactive power, and if that power is then not restored, quickly the voltage on the grid will collapse. And this is what actually caused the famous 13 March 1989 event, which occurred mainly in Quebec. Some of you may have heard about it. So conductors forwarded the GIC to sensitive transformers, and they actually require a certain voltage, amplitude, and frequency to function properly. So there's some automated procedure to save the transformers and other equipment. The power grid was automatically taken out of commission as something called circuit breakers tripped all over Quebec and automatically shut off the power system. But what happened was all this occurred within 90 minutes, and actually it kind of surprised everybody because nobody was really looking at the sun in that way. This is some years ago, you know, and we have really come far since then. And 6 million people lost electrical power for 9 or more hours on. Okay, why is this a problem? Of course, you know, if you don't have power, it's a bit frustrating. If it's cold March in Canada, it's not so fun. Think about hospitals and things. Most of these, of course, have backup transformers. But what it can cost a lot of money, actually. And that's why now with forecasting systems, you are able to say in advance there's a probability there may be a storm that may induce this effect. And then people, the electrical power industry, can take this into account and start shutting down some things that are less important, etc. Okay? So the final example is these SEP events. They are protons, electrons and other ions, heavier, and their energy ranges from some dozen of keVs to a few very high energy giga electron volts. And they may last for minutes to days. They're very sporadic. They're hard to predict. So they're really a problem for also like human space exploration, especially for the astronauts when they go outside the spaceship. So this is just an example, again from 18th October to 7th November during the famous Halloween event. So the lower plot shows the proton flux. So you see there's these SEP events occurring. And the upper plot shows the correlation when there were actually like coronal mass ejections. As I mentioned before, there were also solar flares going on during this time. But it's again to show how we look at these types of images. And actually for education, it's also fun to have the students go in the literature. It's, you know, it's very simple to see, oh yeah, there's a correlation. That means there must be something perhaps going on between these effects. So particles can cause damage both on technical systems. There are two types of technical damage: single event effects, which are basic, is like one particle that ionizes some device when it has enough energy to do so. But there's also an effect called cumulative radiation damage, and that's like I mentioned before, for example, for solar panels over time. They have, for example, displacement damage dose. This is on atom level, so the like electrons, and etc. are displaced, and over time this causes that they're less and less efficient, the solar array. Okay, so I won't talk more here because this I think is more interesting also for the students, because I think most students still nowadays get excited about the prospects of perhaps going to Mars. The most famous, actually, that's used as an example was in 1972. There was a solar proton event. And what was unique about it and why it's famous, it actually happened during the Apollo era. And luckily, it happened between two Apollo missions, 16 and 17. Because again, we didn't really think about this issue. This was back in the 70s, okay? The space era had basically only started recently. And the thing was that simulations, there's a debate, but some simulations say that the dose an astronaut would have received if he or she had been outside the spacecraft doing moonwalking would have been fatal enough basically to kill the astronaut. So, and what do these particles actually do? Again, this is to actually take some biology into the topic matter, because this is why space weather, I like space weather. It covers not just technical issues and scientific issues, but it also covers like medical issues, you know, because actually the particles, they go into the cellular level, and then they, for example, interact and can damage the DNA strings. And let's say over time, of course, if you don't die from it, if you have offspring later, we don't know yet what this can do in the long run. So these are things that are actually studied a lot for future human space exploration. And here's, because people always ask too, what the dose one could perhaps, the limits. So actually there's different age groups. They had this 3% stochastic increase of cancer risk that is used as like identifier of when you may not fly anymore as an astronaut. And then there are different like warning levels for 1 minute, 1 hour, 1 day. For one mission, this is like the max 1 sievert you can receive. This is about 100 rem. Again, to show all these things are taken into consideration. At the moment, most of the comparisons have been done to give estimates for the human health aspect of it. For example, from the nuclear explosions and also at the bombs in Hiroshima, that they are compared for the health risk. But we have to remember those types of radiations are not identical to the radiations, for example, an astronaut will receive. So it's like estimates. So only after now having more information about astronauts that actually have stayed for a while, for example, on the ISS, but also the Russian Mir mission when it was up, we have more information how potentially it can affect human life on longer term. And that brings me to a brief introduction to solar storms, space weather. As I said, there's lots more to tell, but it's just to give you a flavor, and I hope to maybe that you want to go back and look a little in the literature to see how you can use this subject for education. Myself, I have 2 projects that I've been involved in that I use for the schools, and one is for more high school level, and one is more for middle school, end of elementary level. But that's up to you to decide, and actually I feel both projects you can like organize in a way that they can be used for all class levels. It's how you present the information. So the first one is called Exploring Space. This is from actually ESA. They have their Aurora exploration program, which concerns looking into the future with human and robotic exploration. Of course, NASA is also looking into this, all the space agencies, and they all want to go back to Mars, and let's see or not go back, but they want to go to Mars, but of course they want to go back to the moon also. The moon has kind of been put on standby now, I think, for enough years, and if we want to go to Mars one day, no doubt the moon will be the first stepping stone before we go to Mars. And why do we want to go to Mars? Yeah, it's dangerous out there, it costs a lot of money. Basically, I think it's our curiosity as a human race, and we've always wanted to look on the other side of the mountain, one can say. And that's why in the old days we actually started crossing the oceans, and now we cross the oceans in space. So the objective of this small project was, I had this idea one should compare how the first explorers who traversed the oceans, this was during the exploration era, Columbus time, and of course other explorers, to those that will explore space in the future. I thought it was like a nice comparison because of course the elements they will encounter are different, but it's the same type of issues. Okay? So why explore? For 500 years ago there were items such as population pressure. Small villages grew into towns and people started wanting to find other spaces to have their farming or whatever, or to have their new kingdom, depending where you were in the system. So new land. There were many untouched natural resources that people wanted to explore and exploit. And of course, search for knowledge, I think, has always been a common factor. And as I said, to desire to find out what lies on the other side of the ocean. For the space, basically I put the question mark, isn't it the same answers as above? Actually, it is in some respects. We still look for natural resources. I think business is one of the factors that actually pushes a lot. Of course, there's a scientific curiosity to understand what's out there. But there's also more philosophical questions, I think, that have started to come out, like how did life evolve? This is like astrobiology. Where do we come from? What does it all mean? The meaning of life? I mean, why are we here? And as I said, the practical side to space exploration, science, commerce, industry. And finally, I think why I like space a lot too is the international collaboration side of it. We can't do this alone. One nation is not going to go to Mars. I don't believe that, actually. Not with the current financial situation, that's for sure. And that means we have to learn to work together, teamwork. And we have a common subject, a common goal. And I think if everybody had this type of experience like we do here today, or at other meetings, people from all over the world, it would help a lot for peace on this world. I really believe that. So space also, it inspires people, and of course education, it can teach us a lot. So what I did was, I had this high school, it was actually a one-day course. It was organized at a university in the space physics department, and they had asked me to talk about space weather, some type of educational idea. And so the number of students, there were about 9, 10. And what we did, first I gave a brief introduction, very short. What is space weather? What was the objective of this course? Actually, just what I've done now. And then I put them into 3 small groups. So there were like 3 students in each group. And we went through item after item. So I would show them the first item. So if you were going to prepare for the trip, what are the funding, education, and politics, the issues that would be relevant? And first I said, look, what was it like 500 years ago? What did these people have to think about? And then what do you think it is like today if we want to go to Mars? And then they had 5 minutes for brainstorming. First they were a little, I said, yeah, please, let's start. And what I was impressed about was how much knowledge these middle school children actually have. Okay, this was in Belgium, and these were students that were really interested in science and space, but still, it was impressive. So it shows that actually there's a lot on the internet, but also the TV, news, books, and many of the young people read and listen to these informations. Transportation technology used was the next item. Again, I asked them, brainstorm. What type of transportation did they use 500 years ago? Okay, and what do they use now? And so on and so on. The knowledge of the trip, what are the dangers? Of course, we know actually much more about the dangers that we will encounter if we go to Mars than those people did 500 years ago that crossed the oceans. They had no idea what they would encounter. We at least have observations. We know it's a harsh environment out there, but they didn't know that. So they had no idea how should we protect against dangers, which was the next item. For example, there were diseases that they encountered, and unfortunately also brought to the New World. But there were also, plants they had never seen before. They didn't know what was poisonous, what was healthy to, all these types of things. Insects were different. And again, I was impressed with the students, what they could think about. And then, of course, like what I show is to give us an example, the C vitamin issue. Because those days they didn't know that it was important to have your vitamin C, your oranges or whatever, or your supplement. So many people got sick of this, actually, associated disease with lack of C vitamin. Now we know that, but then they had no idea what was going on. So, and all these things, the students, I said, please write them down. So they all did. And then finally, how will the trip benefit humanity? How did it benefit us 500 years ago? How will going to Mars benefit us? Again, they discussed 5 minutes, wrote down. And when they had done this exercise, which took about half an hour, again, it's up to you. If you want half an hour or an hour, I had a time constraint, so it had to be quite quick. Then I asked them, then we went through point to point. I asked one person from each group to stand up and tell what were their conclusions. Again, very impressive. And And I think they enjoyed it too. Once they got into it and were more relaxed, they really enjoyed it. And we went through the 5 points. And then afterwards, after having discussed with both the teacher, so their teacher was also there, the high school teacher, and also I suddenly had this idea, maybe we can write a paper together, a scientific paper, the outcomes of this. And they were like, yeah, like how? Yeah, no. And actually, what came out of it is a paper. It's an editorial type, a technical paper. But what it does, so I co-authored it, and so Ivan van der Berg was the teacher, and then all the students are there. So when they went back to the school the weeks after, I had asked them that they write it up in Word document or whatever text editing, their conclusions, their ideas for each point, and then they send that to me. And based on that, I put everything together in this feature article. In parallel, I contacted, this is the EGU Space Weather Journal, so if you actually go to publications or journals and click on that journal, you will come to it. Unfortunately, this journal you have to pay for. So I'm sure we can maybe find a way, if people are interested, I have a copy of it, electronic form. I discussed with the chief editor, Lulan Zorati, what he thought, and actually he was very positive with it because he said, indeed, it's the next generation, and yeah. So after some editing back and forth, because of course as a feature paper it has to be also written in a way, and we had to emphasize actually also the effects for space radiation, things like that. But all in all, voila, and actually I was really excited that this worked out. It's also something for you to think about, also for other topics you teach, because for the students themselves, it's good for their CV, for one thing, and it gives them experience what it is to write like a short paper, okay? So it's not a science paper, but a feature paper is also important to be able to write, to convey to a larger community.
Norma?
Yeah?
What was the age of a student?
They were around 16, 17. Yeah. This was in the Dutch-speaking part of the Belgium, so actually, to be honest, their English was very good. Yeah, them. And what I did was, after I made the first version, I sent it to the teacher to tell him, please send it to the students, because they should all read it. I may have misunderstood something they wrote, so there was, what do you call it, interaction, like we do a normal paper with co-authors. You know, we send it for their feedback and vice versa. So basically, this feature article is based on their feedback from the exercise. No, I was really, as I say, impressed. They think very large, the young people. So the other activity I've been involved in is called I Love My Son. This is more for 5th grade, 7th grade, again, so from maybe 7 to 10 years old and 10 to 13 years old, depending on how you present the material. This paper, I want to tell you the background actually of I Love My Son. So quite many years ago, Professor Yurdunun Tuleni from Turkey, she had this idea of actually what I Love My Son is. And she started it in Turkey, and then afterwards it became more European, and I got involved with it, and these co-authors too, so from Ukraine and Serbia. And what this is basically a paper, a review paper of these many years, the results that have come out of it, okay, and what we hope it will bring with the future. Because we want that more and more countries get involved in it and more schools get involved in it. This journal, for the moment, is free, and you can actually get to this paper, the PDF file, for free. But you'll have copies of these presentations, I understand. So, but what is I Love My Son? So we have actually made now a website called ilovemyson.org that gives you more background behind the initiative, I Love My Son, how it all started, and also some of the drawings that have been made by the students during the years, information about the sun, pictures of the sun, and actually finally information how to organize your own I Love My Son event. So what it has ended up being that there are two approaches to them. I Love My Son is like, it's when the event is held in a school and when the event is held at a public event like a planetarium or open days when it's a bit more lively, okay? But I'm going to show you the original when it's with the school. So there are three parts to this event. Basically, it's the scientist who will contact the school or knows a teacher who's interested in this. Because it's important that the two actually communicate well together and both really want that this activity is successful. That's how it works best, because in the long run, we hope that the teachers can take over and then do this type of event year after year. So at the school, again, it can take an hour or 2 hours depending on your agenda, the school agenda. You come and we have templates, so the children are asked to draw the sun as they perceive it. So we call this the before lecture drawing. So in reality, the teachers should not tell the students anything about the sun before, okay? So they should, it's only knowledge they know from their own, from other courses or from the TV or whatever. And then afterwards, a short lecture is given on the sun. We have a template lecture now that basically it's only figures, so it can be given in any language. And next to the PPT, there's a small document emphasizing for each slide what we would like, what we think is important, one could convey to the children. And then after this small lecture, the children are asked to draw the sun again. And then you have your after picture. Now, after the school visit, there are also some documents to fill in. This is for statistics, but it's also because what we want to see is in the long run, how much does it depend what the culture of the school? Is it a big city? Is it a town, a village, the school? Do the children come from schools that teach more science? Do they come from schools that are more, we can say, artistic schools? You know, all these types of things to understand when we compare the before and after pictures. The class information document concerns the age of the students, female, male, statistics like that. Did they already know about the sun before? I mean, more than usual, etc. Had they had a class about the sun the year before? Things like that. And then finally, the teacher general impression document, also with oneself. How did you feel the event went? How did, for example, I feel the event went? And with all that, yeah, you have done an I Love My Son event. And actually in the article I showed, we have written, Toulonnet et al., she actually has done a case where she goes back to the school, like the year after, and then compares again the before and after with the first before and after to see how it changes. And she's also actually had one example where she's gone to a school where there were both there's an autistic some children and some non-autistic children, but some of the classes they went to together. And when they did the I Love My Son event also, it was merged together. And she could actually really see, and also discussed with some artists and psychologists later, that some of these children that normally would draw very dark pictures, suddenly they drew light, happy pictures more, like with colors and things. So somehow it influenced these children. We don't know what it means. I mean, it's just one case study, but maybe it's a way to reach some of these children. These were not high-level autistic, it was what you call, I don't know the exact terms, but still, I think it's very promising. Yeah, so before I come to my conclusion slide, I just want to say, again, on this website, I don't have time to show you, but please visit, and there's lots of beautiful pictures the children have performed from these different countries. And I invite you also, if you're interested, to contact me and, do the event. And now we're also putting together a special way that actually, when the pictures have been performed, we ask you make special type of pictures of them, because then it's easier to upload them to our system. But all that is something to be discussed if you're interested in doing the event. So finally, because I have 1 minute left, I have my summary slide. So space weather, as you've seen, it's an interdisciplinary subject covering so many different aspects: science, engineering, medicine, business issues, even philosophical issues. And for me, that's why I find it to be the perfect subject for teaching even classical topics such as math, biology, chemistry, that often children think are, oh, it's difficult or it's boring or stuff. And I think if you have an application side to these topic matters, actually children get more into it. Myself, I remember at university, some of the first math courses I had, I thought, why do I learn these things, you know? Differential equation, what can I use it for? And it was only 2 years later when I had a course in applied math to chemical systems, for example, a nuclear reactor, how it works, I understood why I learned differential equations. So I think already in schools, if one starts teaching math in that way, it will inspire also the children. And also, of course, inspiring the next generation in regard to more career opportunities, scientific, technical. I think we all know there's actually a lack of many young people going into these topics. Many want to go into like business, lawyer, medical doctors, often for, maybe I say not good reasons, money, you know, whereas I think really one should choose one's topic if you have the opportunity, of course, because you enjoy it and like it. And there are many opportunities. You don't have to be a pure academic scientist sitting in front of your computer all day. No. There's so many other things you can also do in respect to, for example, space weather, engineering, medicine, business, that are related, you know. So all these topics have started to merge, which I think is really exciting. And finally, space weather affects us all. So please don't forget space weather. Okay, thank you very much.